We deal with the fifth problem in the collision mechanics series. So let us begin with the problem number 1.169. And the problem is stating particle 1 experiences a perfectly elastic collision with a stationary particle 2. Determine their mass ratio if the first part is stating after a head-on collision the particles fly apart in the opposite directions with equal speed, and in the second part the problem is stating the particles fly apart symmetrically relative to the initial direction of particle 1 with the angle of divergence being 60 degree. So let us begin with the first part of the problem. So in the first part of the problem is stating that we have a particle 1, and this particle 1, which is regarded as m1, is moving with a certain speed, let us say u, and it collides with another particle m2 which is currently at rest or stationary. So this is the initial condition that is mentioned in the problem. And now after collision, the problem is stating that the first particle or the particle of mass m1 is going to rebounce with a certain speed, let us say v, and the particle 2, which we take as m2, is going to move with a speed v in the other direction. So the problem is stating after a head-on collision, the particles fly apart in the opposite directions with equal speed. So this is going to be the final condition, that is before and after collision. So now to solve this problem, we begin with applying momentum conservation. So P initial in the x direction is equal to P final in the x direction or in the direction of motion. And therefore we can say that m1u is equal to m1v in the opposite direction, so we put a negative sign, plus m2v in the forward direction. So from here we can write v equals m1u divided by m2 minus m1. So this is the first equation that we have. Now since the problem involves elastic collision, so we can say that the kinetic energy before the collision is equal to the kinetic energy after collision, that is kinetic energy is also conserved. So if we apply kinetic energy conservation, then we can say that initially the particle is having half m1 u square kinetic energy, and after a while half m1 v square plus half m2 v square. So if we substitute the value of v in this equation from the equation 1, then we can remove all the half. Then if we divide by m1, then we are left with u square equals v square plus m2 by m1 v square. So we need to calculate this ratio m2 by m1, and we will be putting v equals m1u upon m2 minus m1. So therefore we can write this equation as u square equal to 1 plus m2 by m1 times v square. So v square can be written as m1 square u square upon m2 minus m1 squared. So this is the expression that we obtained. This is equation number 2, and then we substitute equation 1 in this expression to obtain a equation like this. And now we can remove this u square term, and on solving we obtain m1 by m2 being equal to 1 by 3. So this is the answer to the first part of the problem. Now in the other part, So we have a second part of this problem. So in the other part of the problem is stating that the particles fly apart symmetrically relative to the initial motion direction of particle 1 with the angle of divergence being 60 degree. So if we draw the condition before and after collision, then we can say that this is the particle m1, which is moving with a speed u, and it collides with a stationary particle m2, which is originally at rest. And then after collision, m1 and m2 are flying apart with making an angle of divergence as 60 degree. So we can say that the two particles are going to move in such a way that if this particle goes with a speed v1, then this particle goes with a speed v2, and the angle between them is 60 degree from the initial direction of motion. So we can say that this angle is equal to 30 degree, and this angle is also equal to 30 degree as the problem is stating. And now, so the particles fly apart symmetrically. So symmetrically, that is, both the angles will be 30 degree, and with the divergence being 60 degree, so the two angle will sum up together to make us the value equal to 60 degree. And over here we have already taken in the first part also that this is taken as the x-axis, and this we will be referring as the y-axis. So if we write the momentum, so this one is particle of mass m1 and this is particle of mass m2. So if we apply momentum conservation in the x direction, so we can say that initial momentum of the particle in the x direction is equal to the final momentum of the particle in the x direction, and hence we can say that m1u is equal to m1 v1 cos 30 degree plus m2 v2 cos 30 degree. So we have this one as equation number 1 for this part of the problem. Now similarly we can write that initial momentum in the y direction is equal to the final momentum in the y direction. So initial momentum in the y direction is equal to the final momentum in the y direction. So we can say that initially in this case, in this scenario, there is no momentum in the y direction, so we write it as 0. And finally there is a cos component in the x direction and sin component in the y direction, so we write it as m1 v1 sin 30 degree upward direction, so we take positive, minus of m2 v2 sin 30 degree in the downward direction. So we get this as equation 2. Now we also have a kinetic energy statement for this problem. So we can also say that since the collision is perfectly elastic, so kinetic energy before collision or kinetic energy initially is going to be equal to kinetic energy finally, and hence, so if we substitute the values, so we can write it as half m1 u squared is equal to half m1 v1 square plus half m2 v2 squared, and this is going to serve us as equation number 3 for this part of the problem. And now if we solve these three equations, which can be simply done by substitution, so on solving we obtain the ratio of m1 by m2. So m1 by m2 turns out to be equal to 2. So this is the second part of the problem which we have discussed. So this is the complete solution for problem number 1.169.